Good evening, everybody. I am here to present to you this lovely foldable about the probability of independent events and dependent events. Hopefully you remember from today's class what the difference is between them. The independent events are when things happen with replacement. So that's like when we pick a marble and we put it back. Dependent events are without replacement. And that's when we take a marble and we keep it and we choose another marble. So here we're picking something and we're putting it back. And here we're taking something and we're keeping it. Very big difference in what it does to our probabilities. Let's go ahead and open up our top flap to discover what it does for us. Okay. Here in independent events, we'll investigate the left-hand side first, and then we'll move to the right. Independent events happen when one event does not affect the outcome of the other. Meaning I pick something, I put it back, I don't have to worry about it anymore. Before we even get into calculating these probabilities, we're first going to decide which are and are not independent. So remember, this is with replacement, which means we put it back. Roll a number cube and toss a coin. Is there any way I can keep a number from a number cube? Is there any way I can keep a side of a coin? There's no way I can keep any one of these, which means they are being replaced. If I roll and get a 3, I could roll and get a 3 again. If I flip a coin and get a heads, I can flip a coin and get a heads again. So this one is indeed independent. Spin a spinner 2 times. Well, I'm not picking up a piece of the spinner. The spinner is the spinner and it always remains the spinner. It will never have a piece of it missing. So this is also independent event. Choosing a red jelly bean from the bag, eating it, and choosing another red jelly bean. If I ate one, how could I possibly put it back? And don't be gross by saying you could throw it up. You can't put it back. You ate it. It's gone forever. So this is not an independent event. Choose a red jelly bean from a bag, replace it, so you're putting it back, and choosing another. This indeed would be an independent event. In order to find the probability of an independent or even a dependent event, we're going to find the probability of both events occurring individually, so like the probability of A and the probability of B, and then we're going to multiply them together. So we're going to multiply the two probabilities. Now let's investigate how this is going to work. Slide over to the right with me, and we're going to do a couple of examples. It says, roll a number cube. Oops. Come over to the right with me. We're going to try a couple of examples. We're going to roll a number cube and toss a coin. So we want to know what's the probability that it lands on heads and a 1. So we want to look at them individually. We want to look at the probability of a heads and the probability of a 1. A cube has 2 sides, so probability of a heads would be 1 out of 2. And a probability of getting a 1 on a number cube, well, a number cube has 1, 2, 3, 4, 5, 6 as its possible outcomes. So that would be 1 out of 6. To find their combined probabilities, we're going to multiply our fractions together, which gives us 1 times 1 is 1, 2 times 6 is 12. So the probability of getting a heads and a 1 is equal to 1/12. Again, we're going to look at these two events individually in order to tell what is the overall probability that I get a tails and an even at the same time. Well, we're going to look at the probability of tails and the probability of an even. Probability of tails is the same as probability of heads because it's 1 out of 2. Probability that we get an even number, let's look at our even numbers. Our even numbers are 2, 4, 6. So probability of even would be 3 out of 6. Now we can simplify this before we multiply, or we can leave it. In this case, I'll leave it. We get 1 times 3, which is 3, and 2 times 6, which is 12. Can we simplify this fraction? We sure can. We can divide top and bottom by 3, giving us 1/4. So the probability of flipping a tails and getting an even together at the same time would be 1/4. I'm hoping that you're catching on to this, and if you're not, have no fear. We're going to practice tomorrow in class a whole bunch. Number 2 says choose a candy from the jar, replace it, again, now you know it's independent, and choose another. Here's our jar. Let's find out how many we have total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 total, which we need to know in order to do any probability. Probability of red, then a red. So the probability of a red at first is 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 12. Now I take that red out and I put it back in. And now I want to say, okay, what's the probability I get a red now? Well, did I eliminate any of the marbles or any of the candies? No. I picked one, I looked at it, I said, oh my God, it's so pretty, and then I put it back in the jar. So there's still 12 total, and there's still 8 reds. To find the combo probability of pulling a red and then a red again, we need to multiply. In this case, it might be a bit easier to simplify first, so let's simplify 8/12. You can divide 8/12 by 4, both of them, but they're the same, so you don't really need to do it twice. And this will become 2/3 times 2/3. Those numbers are a lot easier to deal with. Let's go ahead and multiply across. 2 times 2 is 4. 3 times 3 is 9. Can we simplify that fraction? Nope. So that's our answer. The probability of drawing 2 reds in a row would be 4/9. Now they're asking what would be the probability of picking a red, putting it back in, and then picking a blue. We already know the probability of a red is 2/3 simplified, but now we just need the probability of a blue. There are 1, 2, 3, 4 blues out of 12 possibles. So we have 4 out of 12. I'm going to show you another method just to remind you of like a 6th grade skill. When we multiply, we can cross simplify. 2 goes into itself 1 time and into 12 6 times. Now that's easier multiplication. 1 times 4 is 4. 3 times 6 is 18. Can we simplify further? Sure can. We can divide top and bottom by 2. This will give us a final answer of 2/9. So the probability of picking a red, putting it back, then selecting a blue would be 2/9. Now this is all the situation of picking something and then putting it back. So we're never changing the amount of marbles or candies that are in the jar, or the fronts on a spinner, or the sides of a die. We're never changing those. Now let's close this flap and talk about what happens. Well, what happens when we change the situation? Open it up, and let's discuss what a dependent event is first. A dependent event is an event that happens when one event does affect the outcome of the other. Remember, this is without replacement. Sorry, I went into the number 1 there. This is without replacement. First, now we're going to decide. You should notice that a lot of these situations look a lot like the ones from above. We're going to decide which ones are dependent, which ones have a situation where I'm changing the total, where I'm taking something and I'm never putting it back. Choose a red jelly bean from a bag. Eat it. That's very important. And remember, don't be gross. We're not throwing stuff up. Once you eat it, it's gone. And choose another red jelly bean. Well, this is definitely dependent because I took something, I ate it, and I'm not putting it back. So I'm changing the total. Choose a red jelly bean from a bag, replace it, and choose another red. Well, I put it back, so I didn't change the total. So this is not dependent. That would indeed be independent. Choose a student to leave for lunch, then choose a second student from those remaining. The key here is student is leaving and there's students remaining. If a student leaves, they are gone. So they are no longer a part of your total. This would be dependent because then that changes how many students you have left. Again, just like the independence, we're going to find the probability of these two events occurring by multiplying the probability of each event. This one says the probability of A, which would be the first event, times the probability of B following A. That's an interesting concept because you know that you need to figure out what B is based upon whatever happened in A. I know that sounds quite confusing, but I'm about to make it a little less confusing. Slide over with me. Choose a candy from the jar, eat it, and remember we're not being gross. If we eat it, it's gone. And then we're going to choose another. Now, I'm going to grab a pencil for this because I'm going to need to erase. What is the probability of drawing a red and a red? Well, let's make sure these jars are the same so we don't have to recount. Let's see. Oh, yeah, our two jars look the same, so we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total. The jars are indeed the same. Even if you didn't know that, we could easily find the probability of red. The probability of red would be 1, 2, 3, 4, 5, 6, 7, 8 out of 12. Now, I took one of these reds and I ate it, so it's gone from the jar. How many do I have total now for my second draw? Well, now I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now my total has gone down by 1, and how many reds are remaining? 1, 2, 3, 4, 5, 6, 7, and my reds have gone down. So if I eat a red, it eliminated a red from my original amount and one candy from the total. So if you ate it, it's gone. Now we can multiply these numbers together in order to give us our probability. 8 times 7 is 56, over 12 times 11 is 132. We can simplify the top by dividing by 4. I think we can divide by 4. And that would give us, let's see, 14 on the top and 33 on the bottom. So the probability of drawing a red and then a red when I ate the first red is gone, would be 14 out of 33. All right, we're entering a new situation. So we need to erase our red because we don't know if we ate it yet. We're back to all the candies in the jar. This says the probability of red. We already know the probability of red is 8/12. Then we want to know what's the probability of blue, but not just the probability of blue. What's the probability of blue after I ate a red? So I'll just use the same red. Let's say I picked this red in my first try. So I ate it. It's gone. It's out of the jar. That means I now have how many candies remaining? 11 total possible candies, and how many of them are blue? 1, 2, 3, 4. Notice that I didn't eat a blue, so all my blues are still there, but I did eat a candy, so my total changed. Now we can multiply these to get our probability. The 8 times 4 is 32. 12 times 11 would be 132. Here we can divide both top and bottom by 4. That's a coincidence. That won't always happen. We can divide top and bottom by 4, which would give us 8 over 33. So what's the probability I pick a red and I eat it, and then the next one I pick is a blue? Well, that would be 8 out of 33. Which one is more likely to happen? Oddly, this one. I would have assumed this would have been less likely to happen, but it makes sense considering there are the most reds in the jar. If there were equal numbers of things, then it might be a different story. Let's look at number 2. In a drawer with 4 white socks, 3 blue socks, and 6 red socks, you select a sock put it on your foot so it's no longer in the drawer, and select another. We want to know what's the probability we select a red and then a blue. Well, one thing we need to know is the total number of socks, which in this case would be 4 plus 3 plus 6. Well, what's 4 plus 3 plus 6? 6 plus 4 is 10, plus 3 is 13. 13 socks total. So the probability of a red would be, how many red socks we have? 6 red socks, sorry, I went sideways. 6 red socks out of 13 total socks. Now I took that red sock, I put it on my foot, and I did not put it back in the drawer. So that means I have one less total sock to choose my blue from. So instead of 13, I now have 12 total socks. But did I pick a red one? No. So how many blues do I still have left? I mean, did I pick a red one? Yes. But red isn't blue. So I still have all my blue socks left, which means it would be 3 out of 12. We're going to multiply these together. 6 times 3 is 18 over 13 times 12, which is 156. I could divide top and bottom by 6, which means we get a final answer of 3 out of 26. That means the probability that I will choose a red sock to put on my foot and then a blue sock after I'm already wearing the red sock would be 3 out of 26. Now this is all independent-dependent events. I hope it's a little bit clearer. We're going to practice it some more. Thank you for spending this time with me and putting in your effort. Have a good night.